Hello, I am Ankur Kumar, and in this video I will be explaining all the codes that I have written for the second assignment of my computer vision course. So first of all, I start with importing the basic libraries, which are CV2 and NumPy. Then I simply read and resize the image, and I can also show the image. So this is the image that I will be using for the next few questions. So for the first question, we were asked to compute the backward difference, forward difference, and central difference of this given image. So first of all, I've computed the backward difference in x direction and y direction. For backward difference, I've used the filter 0, -1, and 1. I have used a nested for loop, which is used by this filter to travel across the image and multiply its value with the corresponding image values to get the result. This is the resulting image that I got for backward difference in x direction, and this is the image that I got for backward difference in y direction. These are the matrix formation of backward difference in x and y direction respectively. For the second part, I have computed the forward difference again in x and y direction. I will quickly show the result. This is forward difference in y direction, and this is forward difference in x direction. And similarly, for the third part, I have computed the central difference using the filter -1, 0, and 1. I will again show the results for central difference. So this is central difference in y direction, and this is central difference in x direction. And now we were asked to compute the magnitude and orientation images. So I have used the central difference for computing the magnitude and orientation. For computing the magnitude, I have taken the square of value in x direction and square of value in y direction. I have added them and taken the square root. This is how we compute the magnitude, and the magnitude image that I got is this. This is the magnitude image. And for orientation image, I have taken the tan inverse of the ratio of images in y direction and x direction. I have computed both of these using the central difference in x and y. This is the orientation image. And these are the matrix notation. This is the magnitude image, and this is the orientation image. For the second question, we were asked to compute the Laplacian of Gaussian and difference of Gaussian. So I have computed Laplacian of Gaussian using the inbuilt CV functions, which are Gaussian blur and Laplacian. So Gaussian blur simply blurs the image using the Gaussian filter. This is the resultant of Gaussian blur. It simply blurs the image a little bit. I have used a 3x3 kernel for this purpose, and I have used the Laplacian function to compute the Laplacian, which is just the second derivative after computing the Gaussian. So it computes the Laplacian of Gaussian, which gives us the edges of the image. This is the result that I got after using the Laplacian function from CV2. And after this, I have computed the difference of Gaussian. For difference of Gaussian, I have used Gaussian blur of two different sizes, which is basically Gaussian blur of kernel size 7 and kernel size 5, and then I have subtracted them to get the difference of Gaussian. This is the result of difference of Gaussian. It is similar to edge detection, as it is kind of detecting the edges. And for the last part of this question, we were asked to compute the Gaussian pyramid at different levels. The first level of the Gaussian pyramid is the image itself. So this is the first level, which is the image itself. For the subsequent levels, the image is shrinked in size. For shrinking, I have used this for loop, where I have used a Gaussian filter to blur some pixels of the image, and then use that blurred value, that computed pixel value, to put it in a single pixel in my final reduced image. This is after I have used this is the second level of Gaussian pyramid, which basically reduces the image in half size in both rows and columns. So it basically makes the image 1/4 of the original size. And similarly, for the third and fourth level, the image is reduced further. This is the third level of Gaussian pyramid, and this is the fourth level of Gaussian pyramid. As you can see, the image shrinks in size with increasing levels. These are the matrix notation of first level, second level, third level, and fourth level respectively. And finally, for the fourth question, we were asked to take two images. One image was of an image of an apple and another was an orange, and we were asked to combine these two images. So for this purpose, I have first of all defined a few functions which we will be later using, which are subtract, add, reduce, and expand. So first of all, I have created two lists. First is GAU apple and second is GAU orange. In this list, I originally store the original images of apple and orange, and later in these lists, I will store the Gaussian pyramid images of apple and oranges. So in this for loop, I have computed the Gaussian pyramids, and I have also expanded the images using the expand function which I have defined earlier, and then I have also stored those expanded images in different lists, which are apple expanded and orange expanded. And after this, I have simply subtracted an image from the expanded version of that image, which gives us the Laplacian of this image. And then I have stored that image in a separate list, which is, I have not stored that in any list, but I have merged both the apple and orange Laplacians to get a combined image. And then that image I have stored in this merged list. So using this merged list, which is basically a list of Laplacians of different sizes, I will compute the combined apple and orange image. So after this, I have simply added a base Gaussian image to Laplacians, and doing this, we get the combined apple and orange image. However, for this question, I did not got a result which was as expected. This is the result that I got, but I couldn't find any error in this code, as the logic, according to me, is completely right. But maybe there are some errors in this code. So thank you. That's it for this video.